Hi, I'm here to tell you about Team Tusk. Actually, I'm going to give the first half of the talk, and Jake Crawford, who's the first author on this paper, is going to give the second half. As Daniel so carefully talked about, he set up the problem for us. We were looking for sort of classical and maybe not so classical module structure on these networks. And this problem has been studied extensively in the machine learning community. It's basically just unsupervised community detection because we don't have the biological information we would need because it's been blinded in order to incorporate that into our methods. So we're just looking for things that look like module structure. However, the thing that makes this different from those nice pictures that he showed you of these nice modules is kind of the small world nature of these networks. And by small world, I mean something that in other talks here have been called hairballiness, right? So the fact that these are so small, low diameter networks that are so tangled is what is going to create problems if we want to classify and put nodes together in modules, which things are in their local neighborhood. The problem is in these networks, just about everything is in everything else's local neighborhood. And as a way to quantify that, for each of these networks, we could simply make a histogram which looks at all the shortest path distances between all the points in those networks. So in other words, you're at shortest path distance 1 if you're a direct neighbor, you're at distance 2 if you're a neighbor's neighbor, and so forth. And we get pictures that look like this. So on the first network, the PPI network, this is what the distribution of shortest path distances look like. So you can see everything is like distance 2 or 3 apart, right? So that's pretty tight. And we get similar pictures. This is network 2. This is network 3 by that measure. This is network 4. That's even worse, right? Everything really is distance 2 or 3 apart in that co-expression network. So everything's a neighbor of your neighbor, right? It's less than 6 degrees of separation. This is network 5 and network 6. Okay, so why did we enter this dream challenge? We're not normally part of the dream community. Well, our lab has built a very nice technique for detangling hairballs. So we entered dream to basically test our hairball detangler. And then we were going to say, well, here's the basic idea. Detangle the hairballs, and then use whatever community detection off-the-shelf methods are out there, coupled with your hairball detangler. Plus, there's this extra bipartite subgraph thing I'm going to talk about as well. And the bipartite detangling tool we used is actually our new distance metric that's called DSD, or diffusion state distance. And I'm going to give you a little bit of the overview for it. A lot of people talked in the previous 2 days of this conference about methods that somehow use short random walks. This method also uses short random walks, but in a slightly different way than many of these other methods that you've seen. And so let me give you sort of some high-level insight into what we're doing and why. So again, I said almost everything is distance 2 apart. But our insight is to notice that not all length 2 paths give you the same confidence in similarity. For example, if my only connection between A and B over here is through a hub, then that doesn't really vote that A and B are very similar, compared to when A and B are connected through some low-degree node in the network, right? We think paths through hubs should count for less in terms of inferring some kind of similarity between nodes. So how can we come up with a new distance metric that's different from shortest path that takes this into account when it gives distances between nodes in this network? This is our detangler. So we're going to define, it's missing an exponent of k. For some reason it didn't come up. Define HE exponent k for AB to be the expected number of times a k-step random walk starting at A reaches B, including a zero-length random walk, so you get credit for where you start. Now, if you notice, if we define this random walk, can I get the pointer to work? Can you see a red dot? I cannot see a red dot. All right. Okay, so if you look at the node at A, and we walk for k steps, we're using a completely symmetric random walk, meaning at every step we choose a neighbor with equal probability and walk to that neighbor, and we're going to go for k steps. You notice that if we go from A to B on the right here, then we're very likely to reach B if it's connected by many pass-through low-degree nodes. But if we go through a hub, like in the middle, we're liable to diffuse away into an unrelated node because there's so many nodes that we could choose from in our random walk. So already this measure is sort of showing that A and B should be sort of closer on the picture on the right than they are on the picture on the left. Does everyone understand this? However, this is not yet a distance metric, right? Because first of all, it's not even symmetric. This measure, if you're at the center of the star, you're not very likely to go to A in one step, but if you're at A, you're completely always going to go to the center of the star. So we're not quite done. So the next thing that we do is we define a vector where we set, for every node, we look at its global view. Imagine walking and making these walks and leaving breadcrumbs on the other nodes as we do our k-step random walk. And we're just going to look out at a vector where we measure the number of breadcrumbs to V1, number of breadcrumbs to V2, all the way up to the number of breadcrumbs to Vn, all in this k-step random walk. And then we do the same for our other node B. And this is how what we do is different from what other people do with these random walks. We're going to define the distance, the DSD distance, between A and B to be just the L1 norm of these two vectors. So how does my breadcrumb view of the graph differ from your breadcrumb view of the graph? If we're close in the graph, they should look very similar. If we're far away, they should look very different. Does this make sense? Great. Okay, and in fact, we published this in 2013. We proved that it is a metric, indeed, that it satisfies a triangle inequality. And also it converges as k goes to infinity. It turns out that the later steps of the random walk don't really matter. Once you walk long enough to get lost, then everybody starts leaving the same breadcrumbs in the same pattern. So once the walk mixes, if you know the mathematical terms, once you get the walk to mix, then all the terms past the mixing time are canceled in this difference. Okay? And lo and behold, we get this beautiful histogram. This is for Challenge Network 4, the one we did the best on, according to Daniel's measurements, where it spreads out the distances in this really smooth and beautiful way. And what that allows us to do is, instead of in the shortest path work, we have all this ties, right? We have all the things that are of distance 1. Here we can talk about the first closest neighbor, second closest neighbor, third closest neighbor. And in fact, we applied this to function prediction in yeast at first, and that was just hugely helpful. Okay. So again, our approach is we're going to do this DSD metric on the graph, and then we're going to go and use sort of, now that we've detangled, we're going to use off-the-shelf clustering methods and do various other things to make it fit into the parameter of the challenge, which Jake is about to tell you about. But first, there is also something else. Now, it turns out that computing this DSD can be done in one of two ways. One way is computing it exactly is a little bit in pain. If we had used a cluster, we could have easily done it. It's just matrix inversion. So it turns out the time is proportional to taking the inverse of a matrix. There's well-known matrix algebra. It's like computing the graph Laplacian. It is not very difficult. But we wanted to run on desktop computers. We didn't want to sort of bother with the cloud or the cluster. So we had to approximate the distance in order to produce our matrices. There are two ways we could have done it. We did it both ways, as it turned out. One thing we did was we just walked for 7 steps. It turns out once you walk for about the diameter of the network, you're very, very close to the final converged answer because of the difference in the way this thing converges, like I mentioned. The other thing that we did is, it turns out we have a colleague in the math department who is on our team, Xiaozhi Hu, and he and his graduate students specialize in approximate methods for inverting graph Laplacian. So we also shipped the matrix off to them, and they, believe it or not, did something in MATLAB and shipped it back to us. So that's the other way we inverted some of these matrices. And this is just some of the math about explaining why that it's just equivalent to inverting this matrix. And they showed that even their MATLAB code was massively fast compared to how fast it would be to just invert the matrix even in C. So they have a nice amortized. Though I will say that when we use their matrices on challenge 1, there are some artifacts in the approximation. If you look at network 1, there's that little peak all the way over on the right. That's not quite right. That's an artifact of their approximation. It's not going to matter, as we saw when we tested on the leaderboards. So I just want to say a little bit about this bipartite structure, and then I'm going to turn things over to Jake. So we guessed, it turns out incorrectly, but we maybe got some gain out of a false assumption, that the second PPI network was actually a genetic interactions network. And in genetic interactions, so you guys don't know a genetic interaction, we're just going to put an edge between two genes if the double knockout is non-essential genes, if the double knockout is either sicker or weller than we would have expected based on the single knockouts. Kelly and Eidecker, in a very influential paper in 2005, basically defined this between pathway model, which basically said if you can find physical interactions within two sets of genes, those are your two pathways, and then you have a lot of negative genetic interactions in between, that should be indicative of some kind of functional or module structure of pathways. Now, we didn't have anything labeled, so we couldn't use both physical and genetic interactions at the same time because nobody told us which was which. But we didn't have them superimposed. So even if the first network was a physical interaction network and the second was a genetic, as we suspected, we couldn't have done this method because we couldn't match them up. So instead, we used the method of Brady et al., which came out of our group, which just looks for dense bipartite subgraphs. And in fact, the way we score, so for any set, pairs of sets of genes, small modules of pairs of sets of genes, we're going to say that it is good if there are lots of edges, meaning direct genetic interactions going across, and we're going to take those and we're going to subtract the ones that go within each pathway, and that's going to give us a score for any potential bipartite module. With that, I'm going to hand things over to Jake to tell you sort of the rest of the pieces of our method.
Hi. So I just want to talk a bit about how we implemented this and some of the choices that we made along the way. So the first thing we had to think about was there's this signaling network that has directions. And we wanted to find a way to preserve the directions of the edges, like the information in those. But we also needed to keep the network connected so we could run DSD in a way that actually makes sense. So what we did was we did this thing where we added low-weight back edges where there didn't exist a back edge already. And we compared that to a method where we just treated all the edges as undirected, and it actually gave us better results on the leaderboard rounds. So we stuck with that. Right, so we have this distance matrix from DSD. Now what do we do? So as Daniel said, there are hundreds of methods out there to do this sort of clustering on a distance or similarity matrix or on a graph, whatever. We tried two. We tried this basic edge removal method where we just removed edges that have the highest DSD distance. And we also tried this spectral clustering method. And the spectral clustering did a lot better on the leaderboard rounds, so we stuck with that. So here's the high-level overview of how spectral clustering works. The first thing we need to do is that most of these algorithms take a similarity matrix as input. So we needed to convert our distances to similarities. The way that we chose to do that was using this RBF, or radial basis function kernel. Basically, the idea is that it maps high distance values to lower similarity values. So something that's far apart is going to be less similar than something close together. And once we had that, we ran this spectral clustering, which is just dimension reduction, and then it's k-means in the reduced dimension space. We just used this off-the-shelf implementation in scikit-learn. And we used most of our leaderboard rounds to test different values for k in the k-means, so test different numbers of cluster centers. So here's kind of an example of how we chose our final submissions. So in this case, you can see that we have three. What you want to look at is this NS train value. So we had three submissions that were basically the same on the leaderboards. And in order to distinguish, we used the different FDR levels that the organizers gave us. And so in this case, we kind of want to pick the one with the best scores across all FDR levels. And that hopefully would give us results that make sense on the test data as well. So here's another example where we have scores that are close but not exactly the same. And in this case, we actually picked the one that's not the best scoring on the leaderboards, but it's the most consistent. So now we have DSD, we have a way to cluster the resulting matrix. But the problem is that we need clusters of size between 3 and 100 because that's how the challenge works. And spectral clustering doesn't give any guarantees about the size of the clusters. So how we dealt with that was we just threw out the small clusters, size less than 3. Any large cluster of size greater than 100, we would run spectral clustering again using the same methods recursively with k equals 2 until all the clusters are of size less than 100. And in theory, that doesn't really guarantee us sensible clusters, but in practice, it seemed to give us clusters that made sense. And of the results where we compared the two, we compared split to non-split clusters. Only one of them did worse, and most of them did better. Right. So that describes our method entirely for networks 1, 4, and 6. For networks 2, 3, and 5, we wanted to try this, this looking for these BPM motifs that Lenore described. So, right. So as Lenore said, we're going to look for these BPM motifs. We used a method out of our lab called gene-centric to look for these in an efficient way. And I just want to emphasize again that we don't actually know if these were the modules that scored well for us, but that's something we would like to look at once we have the de-anonymized data after the conference. So now we have these two sets of clusters. We have the clusters that we derived from these BPM motifs, and we have clusters that we got from spectral clustering. How do we merge them? Right, we need a single set of final non-overlapping clusters. So we tried two approaches for doing that. The first one was just this simple greedy approach. So on the left, you can see that we have our set of clusters derived from spectral clustering, and on the right, we have a much smaller set of clusters derived from this gene-centric method. And all we're going to do in this case is we're going to prefer the gene-centric clusters, and we're going to take any spectral cluster that doesn't overlap with any of those. So it's really just a greedy approach. We're just preferring the ones on the right. And we ended up using this for our final submission on network 3. So for networks 2 and 5, we tried this other more conservative method so we have our same spectral clusters on the left, our gene-centric clusters on the right. The first thing we did is we took every node that's clustered in the spectral clusters and not in the gene-centric clusters and put it in one giant cluster. Then we just gave every cluster on both sides an index. So now every node in the final clustering has two clusters that it's in, right? It has a spectral cluster and a gene-centric cluster. And now you can just cluster all of the nodes that are the same in both. So in that sense, it's sort of conservative in that they have to be in the same cluster in both original sets of clusters to be in the same final cluster. And then like before, we're just going to throw out all the small ones. And this was our final submission for networks 2 and 5. Right, so here's what we've got so far. We've got our DSD, we have a way to cluster that matrix, we have a way to correct for the cluster sizes, and we have a way to integrate in these BPM motifs to get a final set of non-overlapping clusters between size 3 and 100. So we're doing well. I just want to describe real quick what we did for Subchallenge 2. We wanted to use the same approach, just using DSD, but we weren't sure what network to run that on. So we just kind of overlaid the networks like this. We just took a kind of a naive union of the networks. And for any edges that were overlapping, we took the maximum of the two weights plus 0.05 to reflect an increased confidence that the edge is not spurious. And then we just used the same DSD plus spectral clustering approach that I described before. And we tried a bunch of different combinations of these networks, and it turned out the union of networks 1, 2, and 4, so that's the two PPI networks plus the co-expression network, ended up doing the best for us. And this is the distribution we get from that network, which also looks pretty good. Right, so in the future, once we get the data after the conference and now the challenge is over, there are some things we'd like to try. In our leaderboard submissions, we tried a few submissions in which we changed the edge weights a little bit to reflect increased or decreased confidence in things, but we didn't have enough submissions to really try a lot of that. So in the future, we'd like to look at that in more detail. We'd also like to, so like I said, there are hundreds of clustering algorithms out there. We kind of arbitrarily chose these two. We'd like to try a lot more in the future and just see sort of what does the best. And we could also test additional methods of combining networks for Subchallenge 2. That's all I've got. Thanks.
So we have time for 1 or 2 questions. It's better than 2.
I was going to ask a two-parter, but I'll choose my favorite part. I was just curious about the gap between the first histograms that Lenore showed, where you're looking at node-node distance as the number of edges, and then these nice distributions you get from DSD, and if maybe just to convince other people who aren't here hearing from you why this works well, that you need to account for multiple paths and all the things that a random walk gives you. You could also run the spectral clustering and everything downstream on just weighted path distances or degree normalized edge weighted path distances, so that even the starting point before you do any random walks, you have a slightly more spread out distribution.
I think that would help. I mean, I think there's no question that if you do something where you're down-weighting hubs and doing this kind of neighborhood thing in any way, that you're going to get better results. I think that's really the take-home message. The nice thing about doing it up front is that all these machine learning methods that other people have built out there take as input a kernel, which is essentially either a similarity matrix, or like you can put 1 over the similarities, or e to the minus, which is what the RBF kernel does. You can just change your similarity to a distance, either way. But then there's all this technology off the shelf that you immediately run with easily, right? You've changed your hairball into something that the machine learning community that doesn't deal with these small networks as much knows how to deal with. And then you could just run all their stuff. So there's in terms of other people developing software, there's a modularity reason why this is kind of elegant. But I agree it would work.
Okay, thanks.